Now that you know how to perform most finishing operations, let's turn our attention to the roughing operations. Most parts begin as a piece of round stock that is larger in diameter than the finished part and longer in length. Our job is to efficiently remove the extra material. Programming a rough turning operation is much easier today than it was in the early years of NC. The old way to rough turn this part would have meant that you would program each movement for each rough pass. So in other words, we would have had to rapid the tool down to our cut diameter, calculate the end point for our rough turn, feed down to that point, feed up off of the part, rapid back to the front of the part, with each pass taking a total of 4 program lines. This meant an awful lot of programming. Today we have multiple repetitive cycles that do all the work for us. In fact, if you can understand programming a finished turning operation, to rough it we really only need to add 2 more lines of program code, and that will magically rough the entire part. When we rough a part, we must remove the material the most efficient way possible. A good roughing cycle, such as the G71 cycle, will provide us with good control over the feed rate, depth of cut, finishing stock allowance for the x-axis, and finishing stock allowance for the z-axis. The ability to change these settings easily is what makes the roughing cycle G71 so powerful. This provides the setup person with an easy way of optimizing the roughing of the part. If you think about it, when we calculate our depth of cut, feed rate, and so forth, when we're writing the program, we're basing this strictly on theory, although based on practical application. But when the part gets down to the machine and the setup person is setting up the job, he may see things that could be done more efficiently, perhaps by taking a greater depth of cut or even a higher feed rate. This is why the G71 cycle is so powerful. It allows the setup person to make changes like this very easily. When we specify the depth of cut for turning, we specify the amount as a radius value. In other words, the depth of cut is the amount of material removed per side on the workpiece. For example, if the depth of cut is 100 thousandths of an inch, the diameter of the part is reduced by 200 thousandths of an inch for each cut. When we specify the finishing stock allowance for the z-axis, we are telling the tool to stay away from the finished part by the amount specified. For example, if we specify a finishing stock allowance for z-axis of 5 thousandths of an inch, the whole cutting pattern for the roughing operation will be shifted 5 thousandths of an inch to the right. When we specify the finishing stock allowance for the x-axis, we are telling the tool to stay away from the finished part by the amount specified, as was the case for z-axis. For example, if we specify a finishing stock allowance for x-axis of 40 thousandths of an inch, the whole cutting pattern for the roughing operation will be shifted 40 thousandths of an inch away. This would mean the part would be 40 thousandths of an inch larger in diameter after the roughing operation is complete. To program the roughing cycle, we only need to program the finish pass and add an extra line or two to define the roughing cycle with G71. To begin, let's select the insert geometry based on our cutting conditions. I have chosen 4140 steel for this particular example part. We are going to be taking 125 thousandths of an inch depth of cut, which means that our diameter will be reduced by 250 thousandths for each pass. I've also chosen a 15 thousandths of an inch per revolution feed rate for this roughing operation. As mentioned earlier, for roughing we want to do this as efficiently as possible. That means we want to keep our depth of cut as high as possible and our feed rate as high as possible. The 125 depth of cut that we have chosen is adequate for our particular machine that we're programming for. For this example, we are assuming that the machine would be an 20 horsepower turning center, which could easily handle an 1/8 inch depth of cut in 4140 steel. Selecting your depth of cut is based upon the workpiece material and how much power it is going to require to machine it. You will really need to refer to different documents or different books that explain to you how to calculate the horsepower based on the cut. Most tooling vendors provide you with slide rules or other formulas or calculators that can help you to determine the horsepower of cut. The feed rate at 15 thousandths per revolution is a fairly good starting point for a roughing feed rate. However, for an efficiency point of view and an optimization for tool life, you want to increase your depth of cut and then increase your feed rate secondary. And that's how you would optimize this cycle down on the machine. If you think you can take a heavier cut, first increase your depth of cut, and then once you achieve the maximum depth of cut that you feel safe with, then you can slowly bring up the feed rate to the point where you are still feeling safe, but yet still machining very efficiently. In our particular example, what we're going to do is look along the left-hand column and find our depth of cut range at 125 thousandths. We will also find our feed rate range along the bottom, which is 15 thousandths, and we will draw a line up from there. And where they converge, the line going from left to right from the 125 thousandths depth of cut, and from bottom to top going from our 15 thousandths per revolution feed rate, where those two lines do converge, that is the insert geometry that we want to use for our roughing application. While we're on this screen, we could also select our insert geometry for our finishing application, and that would fit into the category of MG-UF or possibly MG-LF. Either one would appear to work fine for a finishing application. Now let's get the insert grade that is recommended for our application. Our workpiece material was 4140 steel with an 1/8 inch depth of cut, 15 thousandths per revolution feed rate, and an MG-MG type chip breaker. Going down to the chart, what we're going to do is come down the left-hand column and find our chip breaker, which is labeled MG-MG. Then we're going to come down the column labeled smooth cut. That would be the right-hand side of this chart. And where those two lines converge, coming from left to right from the MG-MG chip breaker and coming down from the smooth cut column, we are going to select our insert grade, which in this case, this company is recommending their grade of KC 9010. Using the information we have so far, we can then determine what the SFM should be. Using the chart below, we know that we're going to be taking a smooth cut, so we'll be selecting our speed in the yellow range shown on the chart below. So we come down to our insert grade along the left-hand side, which is KC 9010, and then we look at the yellow range for smooth cut. And we can see that our range is from 550 to 1100. So we add these two together and divide them by 2 to get our mid starting range. And that would be 825 SFM. But if you notice, there's a note at the bottom of this chart. It says, as the depth of cut increases, decrease the cutting speed. So that would mean that in this range, we would want to favor the higher speed for our finishing applications and the lower speed for our roughing applications. So based on this, in our 125 thousandths depth of cut, what I'm going to do is slow it down just a notch. And that would be, we'll say for this example, 750 SFM, and we'll give that a try and see how well it performs for us. Now that we have our roughing information, let's go back and go through the steps for the finishing application. Now that we have our cutting conditions determined, we need to perform our dimensional math. For this example, we only need to calculate the small diameter for the chamfer and the z-axis ending point of that chamfer. To do this, what we are going to do is work from our 1-inch diameter, which is where that 1/16 by 45 degree chamfer is. So we'll start out with the 1-inch diameter, and we will subtract 0.0625, and again we'll subtract 0.0625, which gives us 0.875, and that would be the starting diameter of that chamfer. And the chamfer is a 45 degree chamfer, so I know that its length and height are identical, as we learned earlier on 45 degree chamfers. So I know that the z endpoint of that chamfer would be z minus 0.0625. Here is the program to rough turn this part. We'll walk you through it kind of briefly right now, and then in the next few slides we will go through a more detailed explanation of some very important aspects of this program. Starting out, line number 200 calls up tool 2 with offset 2, as we have done in the past. Line number 210 puts the machine into constant surface speed mode with G96 at 750 SFM as specified by the S word, and the spindle is turned on in forward rotation with the MO3 command. Line number 220 rapids the tool to X of 3.1 and Z of 0.1 and turns the coolant on. This sets up what is going to be called the convenient starting position for our roughing cycle. Line number 230 is the first line of G71, and that sets up the depth of cut for our roughing operation. In this case, we specify U of 0.125, which is our 125 depth of cut, which reduces the diameter by 250 thousandths for each pass. The R word is the retract amount for the tool when it gets to the end of that pass. A value of 50 thousandths of an inch usually works fairly well for almost every application. Line number 240 is the second line of G71. There is a P word and a Q word. Those specify the line numbers for the beginning and the end of the finished pass definition. Notice in the blue section of the program, the first line is line number N250. So that is where I get our P250 from. The last line of our finished pass definition is line number N320. So therefore that is the end of the finished pass definition. So we use Q320. The finishing stock allowance for the diameter of the part is specified with the U word. In our case, it's U 0.080, which would leave the part 80 thousandths larger in diameter. That would mean a 40 thousandths per side depth of cut for our finishing operation. The W word, W 0.005, specifies that 5 thousandths of finishing stock will be left on all faces. And that feed rate there of F.015 is our roughing feed rate. Going on to line number 250, that is a rapid movement, and it must be a rapid movement. And it takes us down to the smallest diameter that we're going to start cutting from. Line number 260 feeds the tool up to Z0, turns on tool nose radius compensation right with the G42 command, and it is programmed with a feed rate of 6 thousandths per revolution, which is going to be our finishing feed rate. Line number 270 keeps the machine into linear interpolation mode and cuts our first chamfer. Line number 280, still in linear interpolation mode as specified by the GO1 command, will turn the 1 diameter and end our tool at a Z minus 0.5 dimension. Line number 290 back faces up that small shoulder and ends the tool at a diameter of 1.25 inches. Line number 300 will feed the tool along the diameter and stop it at Z minus 0.75 inches. Line number 310 will take the tool and cut along that long tapered surface, leaving the tool at a 3-inch diameter and a Z position of minus 2.421. Line number 320, still in linear interpolation mode, will also turn off tool nose radius compensation with the G40 command and we will feed safely off of the part to a diameter of 3.1 inches. And that's where we want to end our finish pass definition. Line number 330 rapids the tool back to the tool change position of X 4.5 inches in diameter and Z of 3 inches. And finally, line number 340 is our optional stop command. The convenient start position is critical because it sets up the roughing boundary. It is from this point that all the roughing moves are calculated from. If you look in our program, line number 220 is the line that establishes that convenient start position. The convenient start position is based upon the position the tool is at just before the G71 cycle is commanded. What we want to do with that position is we want to be slightly larger than the stock diameter, and we want to be slightly away from the front face of the part. Now that amount, slightly, is kind of a generic term, but what we are looking for is a safe distance and a distance that is great enough for us to safely turn on and off tool nose radius compensation. In our case, if we're using a 31 thousandths tool nose radius, we would be safe because we are moving 100 thousandths both at the end of the path and at the beginning of the path. So our position of 100 thousandths larger in diameter and 100 thousandths away from the front of the part is a good, convenient starting position. Now this position is very, very critical, and hopefully you understand that point, that we must be at the stock diameter plus a little bit and at the rough face of the part plus a little bit before we command the G71 cycle. If you get this position wrong, your roughing cycle will not work correctly. The roughing cycle needs to know what the finished part looks like. The finish pass definition is used to define the finish cutting path. The P and Q words on the G71 cycle identify the starting with the P word and the ending with the Q word lines of the finish pass. Now looking at our program on line number 240, you can see that there's the G71 command with the P word, 250. Now that would be the next line in your program, and that in our case happens to be N250, and that is a rapid movement that takes us from our convenient starting position down to our first cutting diameter. Still in line number 240, looking at the Q word, which in this case is 320, that would be our last movement of the finish pass definition. And that would leave our tool back towards the end of the workpiece or toward the left end of the part, but it would also include turning off tool nose radius compensation and positioning the tool slightly larger than our stock diameter. You will notice that the X position on line number N320, which is X 3.1, is identical to our convenient starting position specified in line number N220, which has an X of 3.1. This next step is very critical. If you do not perform this step properly, we are not certain what type of results you might get. So therefore pay close attention. The first movement after the G71 cycle is defined must be a rapid-only movement on the x-axis. Should you feed during this line, unusual and possibly unexpected movements may occur which may result in a crash. Now let's take a look at the program again. On line number 220, our tool would be at a 3.1 inch diameter and 100 thousandths away from the front of the part. That is our convenient start position. On line number 250, which is the very first line in our finish pass definition as specified by the P word 250 on line number 240. Now you'll notice that that movement on line number 250 is a rapid movement, and it is going to position us at our smallest diameter, which is the starting diameter of our chamfer of 0.875. I know this looks unusual in that we're doing a roughing operation and we are going to be rapiding the tool all the way down to the smallest diameter. However, the G71 cycle is going to take care of all the roughing for us. At this stage of the game, what we are doing is programming the finish pass definition. The G71 will do all the other work for us. The last move of the finish pass definition must leave the tool at the end of the finish pass. Do not program the tool to move back to the front of the part. This is a mistake that beginners will make time and time again. Now let's look at the program and see how this fits. On line number 240, we have our G71 cycle, the second line of its definition, with the P and the Q words. The P word specifying the first line of our finish pass definition, and the Q word specifying the last line of our finish pass definition. Now let's look at line number 320. That command, G01, G40, puts the machine into linear interpolation and turns off tool nose radius compensation, and it positions the tool back at our convenient starting diameter of X 3.1. But I do not, and I repeat, do not rapid the tool back to Z of 0.1. That is not needed here. The G71 cycle will do this for you automatically. If you program that Z movement in there, very strange and very unusual things can happen with the G71 cycle, and this may cause the machine to crash. So get it straight and get it understood right now. At the last line in your finish pass definition, we want to be at our safe position for x-axis, but leave the tool at the end of the finish pass for our z-axis. The radial depth of cut for the roughing passes is specified on the first line of the G71 cycle with the U word. This is a radial depth of cut specification, which means that a 0.125 depth of cut would reduce the diameter of the part by 250 thousandths of an inch. Look down at our program example on line number 230. We have our G71 with our U of 0.125, and that is specifying our depth of cut, and that is on the side of the workpiece. So the diameter would be reduced by 250 thousandths of an inch. Now this is what gives the setup person a lot of control over how this part is roughed. If he feels he can achieve a higher depth of cut, he can simply change this U word to take less roughing passes by taking a deeper cut amount. When the tool reaches the end of a rough pass, the tool will retract away from the part by the amount specified with the R word on the first line of G71. A value of 50 thousandths of an inch is good for most applications. Looking down at our program example, we see that line number 230 is our first line of the G71 definition, and that the R word is specified as R.05, meaning a 50 thousandths of an inch retract at the end of that cut. The G71 cycle must leave stock for the finishing tool to cut. We can specify a different amount of material for each axis. The amount of stock to be left on the x-axis is specified with the U word on the second line of G71. A value of 80 thousandths would leave the diameter of the part 80 thousandths oversize, or in other words, it would be 40 thousandths per side, which is perfect for a finishing cut amount. Looking at the program on line number 240, which is our second line of the G71 cycle, we can see that the U word is specified with 0.080, specifying the part should be 80 thousandths larger in diameter. The amount of stock to be left on the faces, which is the z-axis, is specified with the W word on the second line of G71. A value of 5/1000ths of an inch is a good amount, as we don't want the finishing tool to bury itself at the end of a turning cut. We'll show you what that means in the next slide. Here, I just want you to look again at the program on line number 240, and you will see that our W value is specified with .005, which would mean that there will be 5/1000ths of an inch of stock left on all of the faces of the part. Let's jump ahead for a moment and look at how the finishing tool would interact with our workpiece. In this animation, you can see how the tool buries itself against the face at the end of the turn. This would obviously have very serious effects on the tool and the part, most probably resulting in a crash. A tool with a 5-degree lead angle can handle a 5/1000ths of an inch back-facing cut like shown in the animation here. So in other words, we want to leave a minimal amount of stock on the faces for our finishing tool. And that is where we would specify in the second line of G71 with the W word, leaving 5/1000ths of an inch for finishing stock. Before we jump into the program explanation, I want you to watch closely while I'm narrating this so that you can see what is going to happen after all the roughing passes are performed. You will see the tool come back and take a semi-finishing pass that will smooth out all of the jagged edges left by the roughing operation. This semi-finishing pass will still leave the amount specified for finishing stock. Here again is the completed program, shown to you with the animation running. Now we'll quickly narrate you through this, pointing out some important aspects of this program. Line number 200 calls up tool 2 with offset 2. Line 210 turns the machine on in constant surface speed mode at 750 surface feet per minute in forward rotation. Line number 220 rapids the tool to a diameter of 3.1 inches and a Z position of 100/1000ths away from the face, turning on the coolant. This line, number 220, is what sets up the convenient starting position, as it is the last position prior to the G71 cycle. Line numbers 230 and 240 are the two lines required to define the G71 cycle. On line number 230, we have our first line of G71, with the U word specifying our depth of cut at 125/1000ths of an inch, with a retract amount at the end of each roughing pass of 50/1000ths of an inch. The depth of cut would have to be tailored for each part and each job. The R word specifying the retract amount can be generically set at 50/1000ths of an inch unless there is some very unique case. Line number 240 is the second line of G71, and it specifies the first and last line of our finish pass definition, starting at line number 250 as specified by the P word and ending at line number 320 as specified by the Q word. The U word on this line at .080 is going to leave the part 80/1000ths larger in diameter so that our finishing tool has something to cut. We will also leave 5/1000ths on each face with the W word. And the roughing feed rate is at 15/1000ths per revolution. The finish pass definition begins on line number 250. The very first move is a rapid move, and it must be a rapid move. We are going to rapid down to the smallest diameter, which would be the starting diameter for our chamfer at the front of the part. Line number 260 puts the machine into linear interpolation mode and feeds the tool to Z0, turning on tool nose radius compensation right with the G42 command. This feed rate of F.006 will only be applied for our finishing tool. It has no effect whatsoever for the roughing cycle. Line number 270, 280, 290 300 and 310 are the commands necessary to shape the workpiece into what we want it to be. Line number 320 is the last line in our finishing pass definition, and it will feed the part back up to the same diameter that we started at, shown on line number 220, which was 3.1 inches. We will also turn off our tool nose radius compensation. The other thing that I want you to pay attention to here is notice that in the finish pass definition between N250 and N320, as specified by the P and the Q words, we can turn on tool nose radius compensation and turn it off. We must turn it on and off between the lines specified between P and Q. Line number 330 rapids the tool back to our tool change position, and line number 340 is our optional stop command. Again, I want you to point out to you some very important features here. Line number 220 is our convenient starting position, and that would position the tool slightly larger in diameter and away from the face of the part. There are two lines to specify the G71 cycle. The first line after the G71 cycle is defined must be a rapid movement, and it must be a rapid movement only on the x-axis, taking us to the smallest diameter that we are going to be cutting at. Line number 320 will take us back to the diameter where we started from, 3.1 inches in this example, and if needed it will turn off tool nose radius compensation, but it will not rapid the tool back to the front of the part. The G71 cycle will start the tool at our convenient starting position, and it will end the roughing operation, leaving the tool at the same place it started from, the convenient starting position. And that should wrap it up with the G71 cycle. If you still don't have an understanding of this, you really should back up and review this entire lesson. We will be talking about another application of G71 for boring in a later lesson, and then two very similar routines for roughing. G72, which is a facing operation, and G73, which is a pattern roughing operation. Programming the roughing of a part is similar to all other operations. The G71 cycle makes the programming relatively easy and provides the operator on the machine with great control over the roughing operation. For the roughing operation, the basic steps to perform are: 1. Select a tool. 2. Calculate the speed and feed data. 3. Consider all machining conditions, such as work holding, workpiece material, machine condition, and condition of tooling. 4. Perform the dimensional math as we have done with all other operations. Step number 5, decide on a turret station for our tool. And number 6, write the program and check it carefully. Some